Good evening. Tonight we welcome Ingrid Pelisoli. Ingrid was born in a small city called Rosario in the southernmost state of Brazil, Rio Grande do Sul. She first considered becoming an astronomer at the age of 3. Her grandfather was teaching her to identify the Orion constellation, which shines high and bright during the summer in the southern hemisphere. Ingrid studied at the Federal University of Rio Grande do Sul, doing 2 undergraduate degrees simultaneously, physics and journalism. Graduated in 2012. With that at the highest level, summa cum laude, which means translated from the Latin with the highest praise. She carried her studies, completing a master's degree in astrophysics in 2014 and started a PhD the same year. She obtained a PhD with honours, and her thesis was recognised as the best thesis of 2018 by the Brazilian Astronomical Society. She then moved to Germany and spent 2 years as a postdoc at the University of Potsdam in the Stellar Astrophysics Group, after which she joined the Astronomy and Astrophysics Group at the University of Warwick in November 2020, where she is a Warwick Prize Fellow in the Astronomy and Astrophysics Group. Her main interests are white dwarf and hot subdwarf stars, particularly those in close binary systems, which are often potential supernova 1A progenitors. So can we give a huge welcome to tonight's speaker, Ingrid Pelisoli.
Thank you. Thank you for the lovely introduction. I think I'll share my screen now then. So today I'm here to talk to you about stellar binaries, and in particular I want to talk a bit about how company can change the life of a star. But before I dig into the science, I like to take a few seconds to just look at a nice image of the sky. So that's something I've been doing since I was a kid. The sky has always fascinated me. So here's a nice image of the sky. Some of you might recognize what you're looking at already. I personally am not very good with constellations myself, so I'll connect the dots here for those who can't really identify what they're looking at, like myself. So this is the constellation of Canis Major, or the big dog. And what I would like you to do first to get started is answer a simple question, which is how many stars form the dog in this constellation? In other words, how many stars are connected by lines here? And I'll give you a few seconds to count, and then I want to check the answers and see what you got. Well, it's probably enough time. Usually people count something around 16, sometimes 15, sometimes 17. But what if I were to tell you that Sirius, which is the brighter star in the night sky, as well as this other one here, and another one down there, which might be blocked by my Zoom screen, those stars are actually not just one star. Each of those dots is 2 stars together. Those are binary systems, in particular close binaries, where the 2 stars are too close to each other for our eyes to separate them. So this is just to illustrate that counting stars is really not that straightforward. And one of the reasons for that is because binary systems are actually very common. I can't give you a single number saying 1 out of every X stars are in binaries, and that's because binarity depends a lot on the mass of the star. So what this diagram here is showing is the percentage of stars that are in binaries as a function of the mass of the star. And what we observe is that for stars that are small and red, which are also known as M dwarfs, about 20% are in binaries, so 1 out of 5. For stars like our sun, larger and yellow or orangish, about 50% are in binaries, so 1 out of every 2. For larger and blue stars is at least 80%. So more than 80% or more than 4 out of 5 of these stars are in binary systems. So if we go back to the image I started with, it's actually not a coincidence that the ones that I pointed out here that are in binaries are the bluest ones here. This is just a manifestation of statistics, these are the ones that are more likely to be in binaries, and in this case, they actually are. So now that we know that binary systems are very common, comes the question of how does that change the life of a star, if at all? Before I tell you about the fact of a binary, I thought it would be useful to talk a little bit about how the life of a single star goes. If a star is evolving on its own, what happens? So most stars, they are born with a mass that is up to 10 times the mass of our sun. And what they are doing initially is they are burning hydrogen into helium, into their cores. And what this reaction does is release energy, and that's what prevents the star from collapsing. So there's the gravity trying to make the star collapse, but there's the energy release from hydrogen being burned into helium that prevents that. But eventually the star runs out of hydrogen to burn, so there is no energy being released anymore, and the core of the star starts to collapse. When that happens, it releases energy from the collapse, and the outer layers of the star expand, and that's when it becomes a red giant. With time, the core will have enough pressure to start burning the helium, it will create other elements, and with the release of energy of the reactions that are happening, the star loses its outer layers, and it becomes what is called a white dwarf, which is the most common fossil of stellar evolution. Over 95% of stars will eventually become white dwarfs. If the stars are more massive than 10 times the mass of the sun, they start already very big. They are still doing the same reactions in their core, but once they grow even bigger, so they become supergiants, and they have enough pressure in their cores to continue doing reactions until there is a runaway reaction, and this thing is going to explode as a supernova. When that happens, if the initial mass of the star was less than about 25 times the mass of our sun, it becomes a neutron star. If the mass is larger than that, the whole system collapses into itself. There is nothing that can counterbalance gravity, and the whole thing turns into a black hole. So the point here is essentially that the life of a single star depends simply on its initial mass. If we know the initial mass of a star, we know what it will end up. If it has a mass that is less than 10 times the mass of our sun, it becomes a white dwarf. If it's between 10 and 25, it becomes a neutron star. If it's above that, it becomes a black hole. It's fairly straightforward. If we try to do the same diagram for a binary system, it gets very complicated. But before we had only 3 branches. Now we have, I don't even know how many branches there are here. There are many, many of them. And the reason why this gets complicated is in itself simple. Before we had 1 star with just 1 mass. Now we have 2 stars with 2 masses, but the mass stops being a constant because the stars can throw mass at each other, and they can do this at different points in their lives. So this creates complexity, and we end up with this diagram that is so hard to understand that I don't expect you to really see what's going on here. This is just to illustrate it gets complicated. But if you want to look this up in more detail, the link is on the right over here. But let's try to simplify a bit what is going on here. What is the effect of a companion in the life of a star? So for starters, in many, many cases, it actually makes no difference whatsoever. If you have a binary system where the orbital period of the 2 stars is more than 10 years, so 10 times the orbital period of the Earth around the sun, these 2 stars evolve simply as if there was no other star then. They evolve as single systems. They are too far apart to have any interaction other than just the gravitational interaction of them orbiting each other. If the initial orbital period is less than 10 years, then they are close enough that interaction occurs. And by interaction in this case here, I mean mass being transferred from one star to the other. There's always gravitational interaction between the stars in a binary system. And we don't know exactly how many stars have an initial orbital period that is less than 10 years, but it's something between 25 and 50%. So between a quarter and half of the stars in binary systems interact during a point in their lives. And how can this interaction occur? There is three main ways. One way is called stable mass transfer. As the name suggests, this is a stable interaction. What happens here is that you have the two stars, and let's say one of them evolves to a red giant. And when it does that, what might happen is that its outer layers, the star grows so big that the outer layers go beyond where its gravitational interaction wins over the companion. So the gravitational interaction of the companion starts stealing away mass from this star. And when this occurs in a stable manner, it happens in a way that the companion star can deal with this mass. It can do something with it. It will either accrete it and gain mass, or will burn it in nuclear reactions and get rid of this mass. And the typical outcome when we have this stable mass transfer scenario is that one star will lose its outer layers. It becomes what we call a stripped star. So the core of the star becomes exposed. And because typically some energy gets lost from the system, it carries away angular momentum. So the orbital period of the binary can shrink a little bit. The other situation that we can have is called the common envelope. In this case, we have unstable mass transfer. What happens is that the companion is transferring so much mass, or the donor is transferring so much mass to its companion, that the companion star doesn't know what to do with it. It cannot deal with this amount of mass quickly enough. So the mass starts to accumulate around both stars and forms what we call the common envelope. And the two stars are orbiting inside this envelope, but there will be friction between the stars and the envelope, and this transfers energy from the orbit of the star to the envelope, which eventually gets ejected. And when it does so, it carries away a lot of mass. So at least one of the two stars will lose a lot of mass, and it carries away a lot of energy, a lot of angular momentum from the system. So the orbital period also shrinks, and it can shrink even to a few hours. Finally, the last situation that we can happen is that the two stars merge. And when this happens, they will either form a more massive star, or if the merger product is not stable, this whole thing can explode in a supernova. So in the end, that initially complicated diagram is actually just a combination of these three different processes, but they can happen to the two stars in the system, and they can happen at different stages in the life of these two stars. And they can also happen one after the other. You can have a stable Rush lobe overflow that is followed by a common envelope, or you can have stable Rush lobe overflow that is followed by a merger. So all of these different combinations is what leads to this somewhat complicated diagram, which I hope looks more simple now, because in the end, it's just three different processes, but put together, they look complicated. So now we know that binary stars are abundant. We know how they affect each other. And in fact, to understand this diagram, we actually need input. We need to find binary stars to understand how they interact, so we can improve this diagram, and we can know, once we find a star, what is going to be its future, like we do for single stars. In order to do that, we need to first find the binary stars. So the question becomes, how do we find binary stars? How can we tell if a star is in a binary or not? The most straightforward way is simply point a telescope at it and see if that one dot turns into two. And the example I'm showing here is one of the stars that was in my first slides, is Sirius, so brightest star in the night sky. Sirius, if you point a powerful enough telescope at it, you're going to see it split into two components. One is Sirius A, which is a very bright main sequence star, so a star like our sun, but in this case, a bit hotter, it's bluer. And the other one, its companion, is a white dwarf star, so much fainter and quite tiny. But the separation between Sirius A and Sirius B can actually be up to 30 times the Earth and Sun distance. So this binary system is actually fairly well separated. That's why we can still use amplification to find it. In many cases, the stars are just too close together that even with the most powerful telescopes we have, we can't separate them. So in order to find these very close binaries, which I must say are the most interesting ones because those are more likely to interact, we need to be more creative and use other methods. One of the methods that we can use is monitor the brightness of a star over time and check for any changes in brightness that might be telling us that the star has a companion. And one of the ways we can find a companion is illustrated here, which is with eclipses. So if we have a binary system and one star passes in front of the other, we will block a certain amount of light. And when this happens, we can tell that there is a binary companion. This is the most straightforward way of finding binary systems via monitoring the brightness of a star over time, but it's not the only one. In some cases, you can have a binary system where one of the stars is fairly hot and the other one is cool. And when this happens, the hot star can heat one side of the cooler star. In this diagram here, this is illustrated by the yellow star being the hotter one. And you can see that the blue one, which is the cooler one, has a side that is a lighter shade. That side is the hotter side. So when we see the hotter side of that star, we see a higher amount of flux than when we see the cooler side, because brightness depends on temperature. So by this variation that we see here, we can infer again that we have a binary system, and we can even infer the temperature relationship between the two stars. Another possible effect comes when we have a component in the system that is very high gravity. One classical example are white dwarfs. White dwarfs, they have a mass that is comparable to the sun, but they have a size that is comparable to the Earth. So they have very, very high gravities. They are very dense, and they can cause tidal deformation on the companion, just like the moon can cause tidal deformation on the Earth. So the companion stops being spherical. It has this kind of rugby ball shape. And depending on whether we are seeing the larger side or the smaller side, we get more light coming in our direction. And that causes this variability here that we see on the top. One peculiarity is that you can see that the minima of the light are not the same. And that's because the side facing the companion has this tip here. And this tip is typically cooler. So it's less bright than the rest of the system. So we see more light depending on whether we see the tip or the other side. And that leads to this variability. So that's another way we can tell there's a binary system there. And specifically, that's a way we can tell that there is a very dense object in the system, such as a white dwarf or a neutron star or even a black hole. There's also more unusual behaviors that we can observe in the form of brightness changes. And later on, I'm going to show you some of these more unusual behaviors. So to summarize the way we find binaries with light curves, what we do is we simply measure the brightness of a star that we think might be single or we think might be a binary over a certain period of time. And then we see if any of these effects that I mentioned have been found. If they have been found, then yes, we can say that the system is in a binary. If they have not been found, then we can't really say anything for sure. It might not be a binary, but we can't completely rule out. The reason being that all of these effects depend on the properties of this binary system. For example, eclipses are only going to be seen if the inclination of the binary is favorable. If the two stars are orbiting on the plane of the sky, we're never going to see an eclipse. Irradiation, we are only going to see if there's a temperature difference between the two stars, and we will only see tidal effects if the two stars are very close and if there's a gravity difference over there. So we still need other methods to try to find all of the binary systems. One other more powerful method than simply monitoring brightness is tracking the movement of a star using radial velocities. So this is illustrated here. So when two stars are in a binary system, what happens is not one is orbiting the other, they are both orbiting a common center of mass. And to find the movement of a star, what we do is take the spectrum of a star. The spectrum of a star is simply the light as a function of color. So we take the light of the star and split into its different colors, into its different frequencies. And when we do that for a star, there are two main components. One is the colors on the background, which is the thermal emission of this star. And the other one are these dark lines over here, which are called absorption lines, that are essentially the fingerprint of the chemical elements on the atmosphere of this star. And it works pretty much like a fingerprint. If you see a certain absorption line, you can tell which element this belongs to. And we have very good laboratory measurements of the position of these absorption lines. And this is what we will look for a star that is not moving. These absorption lines will always have the same color, will always have the same frequency. But if the star is moving, then there is something at play called the Doppler effect, which is the same thing that we hear, that we notice when, for example, there's an ambulance approaching, and when we hear a change in the frequency of the siren, or when we see a Formula One car passing by, there's a change in the frequency of that sound. And light does the same thing. When a source of light is moving, the frequency changes as this thing is moving towards or away from you. So if a star is moving, the position of these absorption lines moves together with the star because of this frequency change caused by the Doppler effect. So we can tell that the star is moving. And we can even measure the exact velocity with which it's moving based on the change in the position of these absorption lines. And with that, we can trace the velocity of the star as a function of time and see that it changes periodically, telling us that this star is going back and forth around the center of mass of the system. So that's another way of finding binary stars. To summarize, the way we find binary stars with their velocity is we measure spectra of a star over a certain period of time, and then we check, is the position of the dark lines, of the absorption lines, changing periodically? If it is, yes, we have a binary system. If it's not, again, we're 100% sure that this is not a binary system, because this still has a dependence on inclination. But here, it's a bit more certain than in the case of brightness changes, because in a binary system, there is always going to be radial velocity change, but our capacity to detect radial velocity change is limited, one, by the properties of the binary, especially its inclination. If it's orbiting on the plane, on the sky, the stars are never getting back and forth. They're just going around on the plane, on the sky. And there's also a limitation of our instruments, of how precise we can measure these velocities. Finally, one of the most precise ways of determining if a star is in a binary system is actually measuring its position very, very accurately. The stars are not static in our galaxy. They are orbiting the center of the galaxy. And if they were just doing that, we would see them essentially describing a line on the sky as they move. But as the stars are orbiting the center of the galaxy, the Earth is also orbiting the sun. So what we would see is actually this kind of spiral shape. If at the same time the star is also orbiting another star, there's a third component to be added. So one is the line from the star orbiting the center of the galaxy. The other component is the spiral caused by the orbit of the Earth. But if you see an additional component, which is the red thing in this illustration here, you can see that there's also an orbit of the star around another star. So if we see a deviation from this simple spiral expected by the movement of the Earth, that's another way of telling that the star is in a binary system. So the way we do this is called astrometry, which is accurately measure the position of a star over a certain period of time. And we can do that and then check if it wobbles away from that expected pattern. If it does that, then we can tell that this is a binary system. If it doesn't, we can be almost 100% sure that this is not a binary system. But there is one limitation here, which is our baseline. If the orbital period of the star is very, very long, and there are stars that have orbital periods of even hundreds of years, we would need to observe the system for hundreds of years to find this wobble. So we can only rule out periods of the same scale of our baseline. So we cannot be 100% sure that it's not a binary, but we can rule out many types of binary. So in summary, there's three main ways I showed here that we can use to find binary stars. These are not the only ways, they are the most used ways. Light curves, radio velocities, and the astrometric method. And the complexity kind of increases from one to the other, even it gets harder to explain them. I hope I did a more or less okay job. So with light curves, they are easy enough that you can actually do them from your back garden. If you measure the brightness of a star every night and just plot that, you might be able to find a new binary just by doing that. Radio velocity is a bit more tricky because you need your setup to be really stable. If your telescope is vibrating, you cannot tell the vibration from the telescope from the movement of the star. So for radio velocities, you really need a stable setup. And for astrometry, you need to measure not only the position of that one star over time, you need to measure all of the stars together so you can compare how they move, so you can extract the ones that are wobbling away from the expected pattern. So this typically requires powerful computers and also satellites, because if you do that from within the atmosphere, then the effect of the atmosphere can kind of simulate a wobble. So we require both satellites and good computers to use this last method here. So now that we know these different methods, I'm going to show you some practical examples of my work to show how these methods are applied to actual science. So the first one is a binary system called HD 265435. This is simply its catalog number. HD stands for Henry Draper, who is the name of the person that was organizing this catalog, and this is the number of the star in the catalog. And now what I was doing was I was searching for binary systems just by looking at different light curves until I found this light curve here. And from the pattern of variability here, we can go back to what I showed you at the beginning. And I hope you can recognize that this is very similar to the tidal effect that I showed before. And indeed, in this situation here, what we are seeing is a tidal effect variability. And in this case here, there is one additional interesting aspect is before I mentioned how the depth of the minima can be different. In this system, we also see the height of the maxima are slightly different. I circled here to make it more clear. And this is due to another binary effect, which is called Doppler boosting. And this is actually a relativistic effect. What is happening is when a star is moving towards you, it kind of bends the light rays in your direction. So you can detect more flux from the star when it's moving towards you than when it's moving away. And because this is a relativistic effect, what this tells you is that this star must be moving at very, very high speeds, comparable to the speed of light. So we went and measured the radial velocities of this star. And what is happening here is that it's moving with a speed that reaches 300 kilometers per second. And this is about 0.1% of the speed of light. So not that high, but it's comparable to the speed of light, enough to cause that relativistic effect. And then we can also compare with the radial velocity method that I showed before, and this is only showing you half the curve, but you can see that it goes back and forth. So this is another way of confirming that the system isn't a binary. And then the nicest thing is that because all of these effects depend on the masses and on the orbital properties of the system, we can do modeling to infer what this binary actually looks like. So what I'm showing here is at the top is the light curve. In gray is the original data that we had. In black is just this data combined together to make it more easily to interpret. And in red is the model. And the same thing at the bottom. Here is the velocities in black and the model in red. And you can see that the model describes this very well. So probably what we are inferring about the system is a good interpretation. And what we find is that this system looks something like this. And to be more precise, this is not exactly what the system looks like right now. What the system looks like right now is just 2 dots on the sky. But when I went to the press release department of the university and said, I found 2 dots on the sky, no one was very excited about it. So they asked me, well, what they will do eventually. And what our models tell us is that in about 30 million years, one of the stars will start stealing mass from the other. So this is what the system will look like in about 30 million years, which is way more interesting than what it looks like now. I agree. But the most interesting thing about this system is that we can also determine the masses of the 2 stars. And what we have found out is that in this system, there is a white dwarf that has a mass very similar to the mass of our sun. And the white dwarf is the one that is tidally deforming its companion, which is a stripped star, so a star that has lost its outer layers, and it has a mass of around 60% the mass of our sun. And what the system is doing is the 2 stars are just orbiting each other, but because they are very close to each other, they have an orbital period of only 100 minutes, they are losing energy due to gravitational wave emission, and eventually they will merge. They will merge in about 70 million years, and when they do that, the combined mass of the 2 stars lead to an unstable system that explodes as a supernova. And it's very cool to find new supernovas because we know supernovas happen in other galaxies. We even use them to measure distances and conclude that our universe is expanding. But in our own galaxy, we find very few binary systems that could eventually go supernova. This is one of about a handful of systems that we know will eventually go supernova. So whenever we find one of these that could go supernova, it's a very nice discovery because it confirms that supernova that we see in other galaxies can happen in our own as well. The other example I want to show is a bit of a different one because this one has a funkier light curve that is a bit harder to interpret. So here what I'm showing is again light as a function of time. Here's the time has been normalized by the period of the system. So instead of counting from 0 to 1, 2, 3 seconds or days, we are counting between 0 and the period of the system. So 1 is the period of the system. And if we take this light curve here, this measurement of brightness over time, and compare to the things that I showed you before, let's say, does this look like an eclipse? It doesn't really look like an eclipse, so we can rule that out. It also doesn't look like the reflection or irradiation effect that I mentioned, because this is quite asymmetric, and this effect here is very symmetric. And similarly, we can also say this is not a tidal effect because of the asymmetry. So when this star here, which is called Ayer's-Co, was first observed, people thought this was not a binary system. They thought this was just a single star that was varying on its own. And specifically, they thought these variations here were due to changes in the size of the star. The star was getting bigger and brighter and then contracting back again. And there are a few different types of stars that actually do that. So this star was ignored by astronomers for many years until actually citizen astronomers or amateur astronomers noticed something interesting, which is there is some excess scatter in this curve here. And in particular, this scatter occurs when the star is brighter. When the star is brighter, it's easier to measure it, so we shouldn't expect more scatter when the star is brighter. Doesn't make sense. So what these amateur astronomers did is they pointed their own telescopes at this star and found out that this excess scatter is actually due to some really fast variability that the original light curve was not picking up. And when they found that out, they knew that they had something very interesting in their hands, and they contacted professional or so-called professional astronomers at the University of Warwick, and we pointed our own big telescopes at it, and that's what we found. So this is now a very high resolution light curve of the system, shown in 3 different colors. So one near ultraviolet, green, and then red, then going towards the near infrared. And what you see here is that the star is varying very quickly. These peaks here come every 2 minutes. So every 2 minutes, the star gets brighter and fainter, brighter and fainter. So the excess scatter we were seeing before is simply due to this very quick pulsating or pulsing behavior from this system here. That comes every 2 minutes, like I said. And interestingly, this same behavior that was seen in the optical was also found in radio waves. So if you point a radio telescope at this star, you're also going to see it pulsing every 2 minutes. We know neutron stars do that, but this here is not a neutron star, because neutron stars, we don't really see them in the optical. So this was something new, something different. To get more information, we can take a spectrum and see what is going on in the spectrum of the star. And in this case here, there's something quite interesting happening. So this is a spectrum of the star. Now we have light as a function of wavelength or as a function of frequency. And what you can see here is there is an increasing flux towards the blue, but there is also an increasing flux towards the red. In stars, they are either blue or red. They cannot be both at the same time. So what the spectrum is telling you is that there are actually two stars here. There's a blue star, which is actually a white dwarf, and there is a red star, which is a star like the sun, but smaller, a main sequence star. And in fact, the original variability that we saw, if we take the radial velocities of the system, we can actually conclude that that initial variability was actually due to binarity. But this is such a unique system that it varies in a way that we don't fully understand yet. Why this is asymmetric is very clear. Binary stars typically have symmetric variability, but this one is very asymmetric. And what we think is happening in the system, putting all of the observed properties together, is we think there is a white dwarf that is spinning very fast. Every 2 minutes is spin. And this variation that we see every 2 minutes is due to the spin of the white dwarf, and specifically because it has a very strong magnetic field that shines over the companion every 2 minutes. And that's why we see that increase in brightness all the way from the optical to radio waves, and now it has even been seen in X-rays. So now that we've seen a few different examples of very peculiar binary stars, you might be wondering, well, why do we even study this kind of system? Why are they interesting? I think one important point, which I made at the very beginning, is, well, large fraction of stars are in binary systems. So if we want to understand the evolution of the stars around us, of our galaxy, of the universe, we need to understand the evolution of binary stars. Another reason that I also alluded to is that binary stars are progenitors of supernovae, which are the things we use to understand the expansion of our universe. But we don't really know what kind of things are exploding. We have some guesses. We know there's a white dwarf in there somewhere, but to find the actual progenitors of supernova, we need to observe more binary systems. And finally, you might have heard about detection of gravitational waves from black holes, but binary stars are actually also sources of gravitational waves. We don't detect them right now because the current instruments that we have are not sensitive to the gravitational waves from binary stars. But in the very near future, in about 10 years, there will be an instrument on the sky called LISA that will be detecting the gravitational waves from binary stars. So if we want to understand what this instrument will be detecting, we need to understand binary stars a little bit better. So to summarize with some take-home messages, if you learn one single thing today, I think that thing should be that binary stars are very common. About 20% of red stars and around 80% of blue stars are in binary systems. So next time you're outside and looking at the sky, think about that. If you're looking at a red star, there's a 1 in 5 chance that you're actually seeing 2 stars, not 1. If you're looking at a blue star, there is an over 80% chance that you are actually seeing 2 stars instead of 1. There are many different techniques to find binary stars, including monitoring their brightness over time, using light curves, or with radio velocities, and also with astrometry. And binary stars can have very complex lives. They can merge, cause supernova, and they can also be sources of gravitational waves. So that's it. That's all I had to show you. And if you have any questions, I'm happy to take them.
Ingrid, thank you very much for a very interesting talk, very informative talk. Could I ask you to stop sharing your screen, please?
Yeah.
And I'd like to invite questions, please, and hopefully we'll furnish some answers. So, as usual, digital hand if you're online, throw a 20 at me if you're in the room, or attract my attention in some other way. Have we got anybody with a question? Nothing. Oh, one of our visitors, Graham.
So
If you're speaking to the microphone, which is down here.
don't walk forward.
No, you should be okay.
Okay. If you have a binary system where the plane of the binary is at right angles to the direction you're seeing it, is there any way to detect it's a binary?
If it's in the plane of the sky, if there's any way to detect it. You can still do it with astrometry because the stars are still going to orbiting the center of mass, so they are still going to be going like this. So with astrometry, you can still detect those, but it wouldn't show up on radio velocities and it wouldn't really show up on your light curves.
Okay. Online, Nick Nichols.
I was just wondering, has there been any exoplanets discovered around these binary stars? And if there has, in theory, is it possible for any of them to exist in the habitable zone without having extremes of hot and cold?
That is a very good question, and it's a very active field of research. So there are people out there trying to find planets around binary systems. You do find them, but typically what is happening is that the planet, rather than orbiting the 2 stars, it's orbiting only one of them. It's very hard to have a stable situation where the planet is orbiting the 2 stars. So in the situation that we have, it wouldn't really have very extreme weathers because it's only orbiting this 1 star and the other one doesn't do much to it. But in the situation where it's orbiting the 2 stars, then you would have very extreme situations of weather. Yeah.
Thank you.
Okay, Michael. In the room? Yeah, go ahead.
Is there any system where it's more than just 2 stars? And is it the same methods to find them?
Oh, that was a bit hard to hear. Sorry, can you repeat it maybe a bit closer to the microphone?
Is there any systems where it's more than just 2 stars and is it the same methods to find them?
Yes, there are. So in fact, for the very blue stars that I mentioned, we think that a large fraction of them are actually in triple systems. So rather than being just 2 stars, we have 3 stars. In a few cases, you can have 4, 5, or there's a few famous situations now where you have 6 stars and they are all eclipsing each other. But the way it works is you can't have all of the 6 stars orbiting each other at the same time. That is not stable. So typically what happens is you have pairs of stars that are orbiting each other. So for the system with 6 stars, you have 3 binary systems, and the 3 binary systems are orbiting a common center of mass. If you have 3 stars, normally you have 2 stars orbiting each other, and then you have a third one further out. But there are many situations where you do have more than just 2 stars.
Mark?
You indicated that an orbital period of greater than 10 years, the stars are effectively single stars. What would the effect of one of those stars going nova be? Would that then impact the other star?
For example, if one of them goes supernova.
Yeah.
Yes, that does impact the other star. So what happens if the 2 stars are orbiting each other and one of them blows over, goes supernova, that other star still has all of the energy of the orbit. So what typically will happen is that it's ejected from the system, and sometimes it can be ejected at very, very high speeds. So we do see a few stars in our galaxy that are traveling really, really fast. And the only way we can explain how fast they are traveling is if before they were in a binary system and the companion exploded as a supernova. So we see evidence for that happening in our own galaxy.
Yeah, okay, Matt. Any other questions? Nobody?
Yeah.
Ron?
Yeah, it's just a strange puzzle. I was thinking, you're talking about stars in the galaxy in general. What about stars in things like globular clusters? Are they likely to be binaries, or more frequently binaries, or less frequently binaries?
Another very good question. So in globular clusters, what we see is that they seem to be less frequent in binaries. And we think the reason is because everything is so close together in a globular cluster, it's very hard for two stars to just interact with each other. So eventually they will interact with the other ones and that will break the binary apart. So we do see much lower fractions of binaries in globular clusters. They still exist, but less than just out there in the field of the galaxy.
Okay, I'm looking around the room. I can't see any questions. I can't see anybody who wants to ask a question online. I'm just not on. Oh, sorry. This always happens to me. I always start around this room. Tony.
You were talking about the split between red stars and blue stars in system. Why is there that split?
Why the red ones are less likely to be in binaries than the
Yes.
blue ones?
Yeah.
So that we think that is probably because the color of a star is actually correlated with its mass. So the blue ones are the bigger ones, so they are more massive, so they have a stronger gravity. So it's easier for them to keep their companions close than it is for the red ones, which are smaller. They will more likely lose their companions. So all stars, they do form in groups. Stars are formed typically in open clusters, and with time, because of interaction, they lose their companions. But the blue ones are more likely to keep their companions because they are more massive than the red ones.
So if you're a blue star, you could keep your red companion. But would you say that was a red companion keeping a blue star? How do you classify which way around it is?
So both of them are keeping each other because they are both orbiting a common center of mass. But blue stars, they are more likely to have companions that are also blue stars. So the two of them have strong gravities that are keeping them together.
I think we're going to have to think about that answer. Ingrid. So I'm looking around for any other questions. I can't see anybody in the room. I can't see anybody online. It just leads me to ask everybody to join and give Ingrid a big Mexican sweet and astronomy society. Thank you. Thank you for an excellent talk, Ingrid.
Thank you very much.